All right, let's dive right in. Today, we're going to pull back the curtain on one of the most fundamental building blocks of, well, everything electronic, the digital pin. Ever wondered how a line of code in your computer can actually reach out and make a light blink in the real world? The secret, my friends, is all in that simple but incredibly powerful digital pin.
And this quote, man, it just nails it. The world around us is messy. It's analog with an infinite number of shades and temperatures and sounds. Digital electronics work because engineers made a brilliant decision to just ignore all that complexity. They created a simplified, black and white version of reality. So what do we call this simplification? It's known as the digital abstraction. And at its core, it's all about creating a world that only understands two states. That's it, just two. And we can see exactly what that means with a super simple analogy.
Honestly, you already get this concept. Think about a light in your house. An analog signal is like a dimmer switch, right? You can slide it up and down to get a whole continuous range of brightness. But a digital signal, that's just your standard light switch. It's either on or it's off. There's no in between. Simple as that.
So you might be asking, why would we give up all that nuance? Well, because what we get in return is absolutely massive. The simple on-off system is incredibly tough. It's super resistant to electrical noise. Plus, you can copy a sequence of ons and offs, digital data, perfectly millions, even billions of times with zero degradation. And that gives us the rock-solid reliability that powers everything from your smartphone to a data center. Okay, so how does a circuit actually do this? How does it represent an on and an off, a 1 and a 0? It's not using abstract symbols. It uses something real, something physical you can measure, voltage. And to make sure all the different chips in a system can understand each other, they all have to agree to play by the same set of rules. Let's start with the listener in the conversation, the input pin. For that pin to be absolutely sure it's hearing a high signal, the voltage it sees has to be at least a certain level. We call that threshold VIH, which stands for voltage input high. And on the flip side, for it to be sure it's hearing a low signal, the voltage has to be below a certain maximum level. And you guessed it, we call that VIL, for voltage input low. Any voltage that falls in that gray area between VIL and VIH, that's an undefined no man's land that circuits are designed to stay away from. All right, now for the speaker, the output pin. When it wants to send a high signal, it makes a promise. It guarantees that its voltage will be at least a certain level, and that level is called VOH, or voltage output high. And to send a low signal, it makes the opposite promise. It guarantees the voltage will be no higher than a certain maximum value. We call that VOL, or voltage output low. Now, these four values, these guarantees, are the secret sauce that makes everything work. And here's where the rubber meets the road. This table puts actual concrete numbers to those acronyms for different logic families of chips. And you can see right away the rules for an old-school TTL chip are way different from a modern CMOS chip. This is why you can't just mix and match parts without checking the datasheet. They might be speaking slightly different languages. So here's the really brilliant part. The gap between what the speaker promises to send and what the listener needs to hear, that gap creates a safety buffer. That buffer has a name. It's called the noise margin. It's the amount of electrical junk and interference a signal can pick up before the receiving chip gets confused and misreads a 1 as a 0 or vice versa. Let's make this totally concrete. For a standard 5-volt CMOS chip, the output guarantees a high signal will be at least 4.95 volts. But the input on the other end only needs to see 3.5 volts to understand it as high. That difference, 4.95 minus 3.5, is 1.45 volts. That is a huge safety cushion of noise margin that makes the whole system incredibly robust. All right, so we've got the rules of the game. We understand the language. Now it's time to meet our star player, the general purpose input/output pin. You'll find these guys, better known as GPIO, on pretty much every microcontroller out there. The absolute magic of a GPIO pin is its flexibility. It's a total chameleon. The exact same physical piece of metal on the chip can be a listener, an input, or it can be a speaker, an output. And what decides its role at any given moment? A single line of your code. That's it. So let's start with the pin's first job, being an output. This is where the pin actively takes control, driving things in the outside world, like turning on an LED or telling a motor when to spin.
Now, when it's an output, a pin can do one of two things to make a circuit work. It can source current, which is like opening a valve from the chip's main power supply and pushing electricity out. Or it can sink current, which is like opening a drain to the ground connection, pulling electricity in from the circuit. Both are super useful ways to turn things on and off.
And here is where it all clicks. This is the classic blink example. First, in your code, you tell the pin its job. Pin mode is output. Then, when you digital write that pin high, you're telling it to source current, pushing power through the LED, and boom, it turns on. And digital write low, that just stops the flow, and the LED turns off. Simple software commands creating a direct physical result. So cool. Okay, that's the pin as a speaker. But what about when its job is to listen? To act as an input, sensing the world around it, like figuring out if someone has pressed a button.
Now, this brings us to a really, really important question. It's a trap that gets just about everyone when they're starting out. You've set a pin to be an input, but what if there's nothing actually connected to it? What does it read? Is it high? Is it low? What's the default?
The answer is, it's neither. And it's a huge problem. This condition is called floating. An unconnected input pin is just hanging out there in the breeze, and it acts like a tiny antenna picking up all the stray electrical noise in the room. Your readings will be completely random and unpredictable, causing the weirdest bugs in your project.
So how do we fix this? Well, with something beautifully simple, a pull-up resistor. All this does is provide a weak, gentle connection from the input pin to the positive voltage supply. It gently pulls the pin up to a default high state, so it's never just left floating. It now has a stable, predictable state to return to. So check out the smart way to read a button. We wire the button so that pressing it connects our pin to ground. Then with a single magical command, input pull-up, we tell the pin two things: be an input and turn on your built-in pull-up resistor. Now, the pin will read high by default because of the pull-up, but when you press that button, you connect it directly to ground, which easily overpowers the weak pull-up, and the pin reads low. No floating, no ambiguity, just a clean, reliable reading.
Of course, the world isn't always as simple as one pin talking to one component. Sometimes you need multiple devices to share the same wire to communicate. For that to work, we need one more trick up our sleeve.
And that trick is a third state, known as high impedance, or sometimes just Z. You can think of the state as the pin electrically disconnecting itself from the wire. It's not driving high, it's not driving low, it's effectively just gone. And this is absolutely crucial for things like a shared data bus, where you have multiple chips hooked up to the same lines. Only one chip can talk at a time, so all the others put their pins into this high impedance state so they don't interfere.
So after all that, what's the one thing you should really take away? It's this. A digital pin isn't just a piece of hardware. It is the fundamental, magical bridge between the clean, abstract world of software and the messy, physical world we all live in. If you can master its rules, you've unlocked the power to make your code reach out and truly change reality.